Okay, so yeah, welcome back to CS580 computer graphics. So last time we were discussing some kind of the ideas about the Monte Carlo the estimator and also how we can apply this kind of a technique for the direct illumination to compute the reflection with the rendering the equation. So last time we discussed some basic idea about the importance sampling, which was the case that if we basically draw the samples based on some kind of the probability distribution, then depending on like which probability distribution that we choose, actually we can say that the estimator can have some basically faster convergence or slow the convergence depending on which the probability distribution that we choose, right? So the best option might be is that if we choose the probability distribution, which has the similar shape with the function that we are basically taking is the integral, then we can get the best kind of the convergence, the rate. So yeah, and once we basically choose any kind of the probability density function, also the question is that how we can also draw the samples based on the probability distribution. So the basic idea for that was basically using the technique called the inverse transform desampling. So this was the case that if we can basically compute the cumulative distribution the function from the probability density function and also take the inverse of the CDF, then we can basically draw some kind of the samples from the uniform distribution in the range from the 0 to 1 and basically map this sample into the domain. They were taking basically the samples, actually drawing the samples using the inverse of the CDF, which means that we should be able to compute not only the CDF, but also the inverse of the CDF, basically to draw the samples based on the probability distribution. So this was basically the basic idea, the fundamental idea of the importance sampling. And so the question is that how we can apply this kind of the idea into the reflection equation. So basically what we are doing in our ray tracing system is basically all about basically computing some kind of interval. So the formulation is basically designed in terms of like taking the sum of some emission of the light from the point that we are calculating the reflection, and also integrating all the incoming radiance from all directions, and then basically compute some kind of reflection using our given the BRDF function, and also taking the integral of that. So that becomes the outgoing kind of the radiance that we are also calculating. So this is basically the overall like computing some kind of integral. And here the basic idea is that how we can also apply the Monte Carlo estimate, the idea to compute those kind of things. So we have also seen kind of the two different cases in terms of like computing this integral. The first was basically the case that we are sampling the solid angles, and the other one was basically solely sampling the points over the kind of the area when we assume that the light source is given as kind of some area light. So those are kind of like two different ways. And in this specific example, that we are basically having this kind of area of the light source, the good thing of like sampling the points over the area of the light source was that we can basically takes up all the kind of rays that will basically contribute to the computation of the outgoing the radiance. While the kind of the limitation, like kind of like taking the samples of the solid angle, was that many of the rays will not basically hit the light source, which means that those rays will not contribute to the kind of computation of the reflection. So that's why basically we can get some kind of the better the convergence rate with the area desampling on the right hand side, while we are basically having some kind of the higher the variance in the solid angle samples because of some many kind of the cases that the rays are not basically hitting the area the light source. So those are like two different ways that we can basically define some kind of estimator for the reflection equation in terms of like sampling the solid angles and sampling the points over the area. So depending on which estimator we choose, actually we can get some kind of the different convergence rates. And these are actually some kind of the examples of doing some sort of the importance sampling. So we are not basically defining some kind of physical some kind of the probability density function for the importance sampling, but basically we are sampling over the points over the area of the light in terms of that we take some more rays that can really contribute to the final computation of the interval. So this was kind of some practical way that we can do some kind of importance sampling. Any questions for the topics that we discussed last time? So the plans for today is that we are going to discuss a little bit more kind of things about this kind of like direct the illumination, and then we're gonna move on to the global illumination. So one thing that we are going to discuss a little bit more about the direct illumination is basically the multiple importance sampling, which is importance sampling. Yeah. So here the basic question is that, so in the previous slide, we have seen that the area the sampling is better than the the solid angle sampling in that specific case. But is it always true for any other cases as well? So what we are going to see is that let's briefly to basically revisit the importance sampling. So the basic idea for the importance sampling was that to estimate integral of the function the f here, what we are going to do is that we are going to choose a sampling the probability the density function dpx, which is close to the some kind of function which is proportional to the function that we're integrating, right? But the case that we are going to see for today is that what if we are taking integral of the function, which can be decomposed into the two functions. So let's say like we are taking the integral of the f function here, which can be actually represented as the product of the f1 and the f2. And let's say that f1 and both of the f1 and the f2 are basically relatively the simple function, and we also have the information about those the functions, while the product of like these two can be some a kind of a highly complex function. So for these kind of the cases, what the kind of the best way that we are basically doing some kind of importance sampling. So what we kind of some real example of this case in our some kind of rendering the equation. So if we go back to our rendering the equation, so we can see that the rendering equation actually can be seen as kind of the taking integral of the product of the BRDF and the light source, the incoming radiance function, right? And also for the both the BRDF and also the light the source the function, these are kind of the given information, right? So we have all the information about like where the light the sources are basically placed in the scene. That is basically defining the incoming the radiance the function, right? And also the BRDF is kind of the material information for the surface, and this is also kind of the user defined information. So basically, and also typically these two functions are relatively like simpler than the product of like these two. So for those kind of cases, what is kind of the best way we can do some kind of the importance sampling. So this is kind of the basic question here. So one of the things that we can think about might be is that like, yeah, so we know these kind of the two components and these two functions basically some relatively simple function. So let's think about like making some kind of the sampling distribution, which is close to the each of the function, which means that we can somehow define some kind of some sampling the distribution function, which is proportional to the either the BRDF or either the light source, right? So either the BRDF basically means that given some kind of the outgoing direction, we can see what are the kind of the some solid angle directions that is basically giving some kind of the more contribution to that specific the outgoing direction. And so based on this kind of the some concentration, like where the most of the lights are coming from that are basically reflected to that specific direction, we can do some kind of the importance sampling. Or we can also do some kind of importance sampling based on the light source, because if we know the kind of information about the light source, as we have done in the previous slide, we can basically sample the points or the surface of the light source, right? So those are basically the two options. So when you have like this kind of the two strategies, so like sampling the points, for these kind of the two cases, let's say for the left case, the yellow, basically the yellow things are basically representing some light source. So on the left-hand side, we are having this kind of some long the light source, which looks like some kind of the area light in the 3D space, where the line in the 2D space, and also very glossy the reflection the BRDF, which is almost close to the perfect spectral reflection. While on the right-hand side, we are having some very tiny the light source, which almost looks like some kind of the point light source with some kind of the wider distribution with the BRDF. So for both of the cases, when you use the two different sampling strategy, like one is sampling based on the BRDF and one is like sampling based on the light source, which one seems the better for each of the cases? Let's think about this. Yeah, so this is actually a simple question, right? So as you can see, the left-hand side, obviously it'd be better to sample based on the BRDF because we can see that some of the lights that are coming from some specific direction is mostly contributing to the computation of the outgoing irradiance, which means that we don't need to basically shoot many rays into some random direction, but we just need to sample to the kind of the direction that we can see some kind of the most of the kind of the contribution to the outgoing resource. This is basically the case that we are having some kind of the glossy reflection, which is actually almost close to some perfect the specular reflection, which means that the direction coming from there, so the lights coming from that directions are mostly basically important kind of the lights for the kind of the final computation. While we have this kind of a case on the right hand side, this is the case that we are having some kind of the very tiny the light source, which almost looks like some kind of the point light source, which means that when you also kind of the sample based on the BRDF, most of the basically rays will not basically hit the light source, which means that these rays will not basically be basically counted in the final decomputation. So in this case, obviously, it's better to basically sample based on basically the light source, which is the case that we are sampling the points over the light source. Right? So as you can see, depending on some kind of some arrangement of this kind of the scenes, and also depending on the BRDF functions for each of the points of these surfaces, this strategy can be changed. So we can choose like sampling based on the BRDF, sampling based on the light source, but which is kind of some kind of the manual things, right? So it sounds like we need to do this kind of making some kind of decisional, like choosing the strategy depending on how these scenes are basically arranged and how also all the surfaces have some kind of the some meteorological properties. So here the question might be is that what the kind of the best way that we can have some kind of the some unified some strategy of the sampling that can be basically applied to any kind of situation, right? So here basically what we can see is that more specifically, if we have this kind of some the function f which can be decomposed into the f1 to the f2. So those cases, if we choose like one of the kind of the function and also find a probability density function which is basically proportional to that function. So let's say like we are picking some kind of the sample distribution the p1, which is basically proportional to the f1. Obviously, even in some kind of the practical cases, it's obviously possible to pick some kind of the probability the distribution, which is perfectly proportional to some kind of any function. But let's even assume that we can do that. Like we can basically find some probability density function, which is basically perfectly proportional to one of the functions. Let's say that's the f1 in this case. But still, in this case, what we can basically see is that then the variance of the kind of the output becomes also the proportional to the variance of the function the f2 here, which may be high, right? So actually, like choosing the sampling the distribution which is following one of the functions may not be the kind of the best strategy for most of the cases. So this is really kind of some practical kind of the issues that we can see in many kind of the rendering the processes. So actually, these are two different images, which is like using one of the sampling this strategy. Like one is sampling based on the BRDF, and the one is sampling based on the light source. And can you tell like which one is like rendered using which sampling this strategy? So actually, these images show that none of these two is kind of the ideal, like the sampling strategy in this specific case. But when you choose one of the sampling the idea, we can get some kind of different kind of the outputs, as you can see here. Yeah, so as you can see, yeah, left is the case that we are using the light importance sampling. So over the image is basically the brighter, while it is not basically, precisely, capturing this kind of the glossy reflection, the effect over the surface of the car, right? On the right-hand side, we can see that the metrology property of the car surface is better captured with the BRDM importance sampling, while the over the image is darker than the left one because it is not sampling from the light source, right? So these are basically the differences depending on like which sampling the strategy that you choose. Makes sense. Cool. So then here the question is that how can we make some kind of the some sort of the universal, some kind of the importance the sampling the idea that can be applied to the any kind of the situation without doing some kind of the manual sort of the fine tuning of the sampling the strategy. So here basically what we can think about is that let's assume the cases that we are having the n different the sampling this strategy, which means that we have the n different the sampling the probability density function, which are basically denoted as the pi, and we are thinking of like drawing the ni, the number of the samples for each of the probability distribution. So for those cases, what we're going to do is that we are going to define the multi-sample estimator like this. So this is kind of the similar with the Monte Carlo the estimates, but we are basically having this kind of the new the weighting the function here. And also here, we are going to define the weight function in a way that for the same kind of sample X here, the sum of the weights becomes one over the all the probability the density function. So this is the condition, and also the weight function should be zero, wherever basically the probability becomes zero. So if we can basically define this kind of the weighted function, then we can also define this kind of multi-sample the estimator. And the good thing with the Monte Carlo estimator that we have seen the previous lecture is that the Monte Carlo estimator is basically a unbiased the estimator, right? So that's a kind of the good thing in terms that we can see that it will basically see some kind of the expected value, which is the same with the true value, right? So here the thing, yeah, so also one more thing is that here the weights basically do not need to be constant. So we can have some kind of the constant the weights for whatever the sample that we have, we can have the constant weights, but it does need to be some kind of the constant weights. Actually, it's better that we are having some kind of the weights that are basically being adjusted depending on the sample. So let's think about that we are having this kind of the weighted function. Then here the question is that whether this kind of the multi-sample estimator is also a unbiased the estimator. So can you quickly check whether this kind of the estimator also has the expected value, which basically is equivalent to the so the integral of the function that we are calculating? need more time? Yeah, maybe you can check this out after the lecture. So let me first move on. So you can also I'm also going to post all the slides in the Slack later. So yeah, I guess you can easily get this kind of the results from the rules that we also have discussed in the previous lecture. So yeah, basically it becomes like taking the expected value for this term and like these two probably the for the samples are canceled out and also these are canceled out because like taking some kind of average. And then this is basically coming from the property of the weighting function that we are defining. So this also becomes one, then we can see that actually becomes the another the unbiased the estimator. So let's check this out after the you can check this out after the lecture. I'm going to post all the slides. So yeah, let's first move on. So yeah, because here the main question might be is that how we can choose the weight function or the weighting function in this case. Actually, there can be multiple ways that we can choose some kind of the weighting function. And actually, we can choose the weight function based on the kind of the situation that we are seeing, based on the arrangement of the objects and also based on the BRDF of the kind of the metrology properties of the surfaces. And one simple kind of some heuristic way that is basically practically used in many kinds of the rendering pipeline is basically this the balance heuristic, which is defined like this. So you can see this formulation. This is basically defined as like choosing the weight function here. It's kind of like taking the product of the number of the samples and the probability, and also dividing this with the sum of the product of the number of the samples and the probability. So let's also do one more kind of quick things. So can you also quickly rewrite the following the multi-sample the estimator with the above the weighting function, and let's see how it looks like, and also what's the meaning of like having this kind of the balance heuristic. So can you quickly rewrite? So basically, if we see the mean of like disability heuristic, this is actually nothing. But when you basically see that, assume that the number of samples for each of the sampling, the probability density function are basically all the same, then we can see that this is nothing but we are basically seeing some kind of the relative the probability of the samples for each of the density function, right? So when we basically see that the sample has the higher probability with one specific the PDF with the probability density function, then we basically increase the weights, which is quite obvious, right? So this is kind of like very simple kind of the trick in terms of that we are basically adapting this kind of the weight based on kind of the probability of the samples for each of the sampling this strategy and taking some kind of the normalize this probability in a way that the weight becomes the sum of the weights over the PDF becomes to one. That is also giving us some kind of the unbiased the estimator. Right. Basically, very simple the idea. Then we can see that we can rewrite the same estimator with this specific the weighting function. Then we get results like this. Here, basically, I just did nothing but like dividing 1 over n here, and in a way that we can see that this becomes some kind of a ratio. The number of samples over the total number of samples. N is basically the total number of samples. Right? So we get this. So what we can see is that after we rewrite everything, we can see that actually this becomes the typical, the standard, the Monte Carlo estimator, while basically making some kind of the another the PDF that looks like this. So this you can see that this becomes some kind of the so some sort of the weighted average of all the kind of the PDFs that we have. So this is the very simple the idea in terms of like doing some kind of the adaptation of the weighting based on the PDF. And while this is really simple kind of trick that we can very easily implement, what we can also basically prove is that so let's think about like this kind of a two estimator. Like F is the typical the multi-sample the estimator with some kind of any arbitrary weight function. And let's say f hat is basically a multi-sample estimator with some kind of the balanced heuristic, the weighting function that we have. Then we can see that the gap of the variance of these two estimators basically have this kind of the upper bound, as you can see here. We can also find the proof of this kind of the formulation in this link here. But before we see some kind of the proof of like this kind of the formulation, let's see. So what does this mean? When you see this kind of the upper bound of the gap of these two variances, what would be the meaning of that? We are seeing this kind of the upper bound of the gap. Well, basically, what we can see is that the right-hand side of this term is always positive, right? So the minimum number of the ni should be equal or smaller the sum of the ni, right? This means that this should be bigger, and this is squared, which means that the right-hand side should be always positive, right? And there is like positive the amount of the gap when you take the difference from the variance of the balance heuristic weight function, the multi-sampled estimate with the balance heuristic weight function with some any arbitrary weight function, which means that actually the variance of the the multi-sampled estimator with the balance heuristic weight function can be bigger than the variance of the some estimator with some arbitrary weighting function, right? So this does not mean that the variance of the f hat is smaller than the variance of the arbitrary the estimator f. Actually, it should be bigger or the same. So actually, what we can see from this is that this does not actually say that the variance of the f hat is smaller than the variance of the f. But it's actually basically the estimator with the arbitrary weight function. So here, basically, the question is that when you take this kind of the balance heuristic as kind of our weighted function, would there be any kind of the other ways that we can define the weighted function? And can this kind of the other the weighted function be better than the balanced heuristic, right? So basically here the question is how good the balanced heuristic is, right? So here basically the thing is that there can be some kind of some arbitrary the weight function for the multi-sample estimator, but still the gap between these two is basically bounded by this amount of the kind of some quantity, which means that when you basically pick any kind of find some kind of the some kind of the weighted function, it cannot basically significantly decrease the variance more than some kind of the variance of the kind of the estimator with the balanced heuristic, which means that still while we can see some kind of the improvement in terms like reducing the variance of the estimator by choosing some kind of the better the weighting function, still the kind of the improvement will be bounded by this amount, right? So we are seeing this kind of some kind of the upper bound, upper limit in terms of like making some kind of the improvement from some kind of the balance heuristic with some kind of the another kind of weight function, which means that the balance heuristic is kind of the good enough in terms of like having this kind of the small amount of kind of the gap with some kind of the another the upper bound of the gap with the arbitrary estimator. And also the thing is that even this gap get closer to zero as we have some more the number of the samples for it to be the probability density function. As you can see in this term, as we see that the ni becomes kind of larger and larger and larger, these two, the difference between these two will get closer to the zero, which means that also the gap between the estimator with the balanced heuristic and also the estimator with some other the weighting functions. The difference between these two in the variance will be basically decreased with this amount of the upper limit. So that's the meaning of like these equations. So please check this out. So yeah, so these are basically some basic idea of the like multiple the importance sampling. So if we see some kind of the comparison with the different the sampling this strategy. So the top left is the case that we are basically doing some kind of the uniform the sampling. And the second, the top right is the case that we are taking the light importance sampling, and also the bottom left is the case that we are taking the BRDF, the importance sampling. So when you typically take some kind of a multiple the importance sampling, which incorporates both the BRDF and the light source in the Monte Carlo estimate, the computation, we can see that we can get some better results in terms like having some kind of the bright image, which basically captures the light information correctly, and also seeing all this kind of some glossiness of the surface that also captures the BRDF correctly as well. So this is kind of the basic idea of like the multiple the importance sampling, and we will be able to see that many of the kind of the ray tracing the pipeline basically utilize this kind of the idea for the Monte Carlo estimated computation. Any questions about the multiple importance sampling? So for the formulation that we had in the previous slides, I recommend you to check out some more details and see what's the meaning of each of the formulation. And also, if you have some other questions, please feel free to post the questions on Slack. So this was kind of the last component about the direct illumination. And then now we are moving on to the global illumination. So what's the difference between the direct illumination and the global illumination? So in the lecture in some weeks ago, we have seen this kind of the figure that shows some kind of the some conceptual idea about the ray tracing. So the direct illumination is the case that we only basically consider some kind of ray casting, basically shooting the ray from the pixel of the image plane and seeing the first intersection, the points. And at that point, we also shoot the ray to the light source in terms like converting the reflection at the kind of first intersection, the point. So if we only incorporate all this information to determine the final the light information coming into the pixel, that becomes kind of the ray casting case, and that becomes the direct illumination, the case that we have seen in the previous slides. But what we also have seen in the previous lecture is that actually what we want to do in the kind of the ray tracing is basically not just like taking into account the single points of the first intersection, but we also shoot the secondary ray, which is basically tracing kind of the path of the lights in the backwards in terms of that we are actually incorporating some multiple the bounces of the lights over some kind of the multiple the surface points. So the idea of the global illumination is that how we are going to also incorporate all these kind of the secondary rays in terms that we really basically trace the lights with some kind of the multiple reflections over the surface along the way that we are basically reaching to the light source with some kind of the multiple bounces. So this computation basically becomes like way more complicated. We're gonna see some kind of the basic idea and basically how we're gonna calculate those kind of things. And before we see some kind of some ideas and how we're gonna calculate all these kind of things, let's first see some kind of the examples. So this is basically kind of the case that we are having the zero bounce, which means that no reflection over the surface. So we only basically care about some kind of information, which is basically directly coming from the light source. So we can only see the light source in this case, right? We only care about the light emission in this case. And if we start to see some kind of the one bounce, which is basically the direct illumination case, then we can start to see some kind of the regions, which is basically visible from both the camera perspective and also from the light source perspective, right? So when you can see that the light can basically come from the light source to any the point and also to the pixel in the image plane, then those basically the points will be basically considered in the final computation of the image, right? So now we are seeing some kind of regions that are basically visible from both of the camera and the light source, right? But still, like the parts of the regions are basically very dark, while this is not the real case. In some kind of real things, we can also see that from the sunlight coming from the window, we can see that the parts of the scene also can become the bright, right? So if we start to increase the number of the bounces that we are basically shooting the secondary ray and basically tracing the lights in the scene, then we can see that the scene becomes the brighter like this. And when you have some more the bounces, you can see that we can some kind of the more realistic the image like this. And after like 8 bounces, like we can see this kind of outputs, which really have some kind of the more accurate and precise the simulation of the light, the reflections, right? Makes sense? So this is another example with a more complex scene. So if you see a point here, a P point here, which is very dark because like this point on the pillar is basically behind the kind of some other kind of things from the light source from the sunlight, right? So basically this point P is basically occluded by the pillar from the light source. So when you only care about the direct illumination, this point becomes very dark like this. Actually, this is not the real case, right? So in the environment, we can see it actually, this point also have some kind of the lights from some kind of the multiple reflections from the other places. So if we start to incorporate some kind of the indirect illumination with some kind of the multiple bounces or some reflections over the surface, we can see that the overall scene becomes the bright like this. So this is also results with the 16 the bounces of some kind of the global illumination. Then we can see that some of the lights actually can reach to this point with some kind of the reflections over this thing. does it look more realistic? So this is another example, which is created by the ray tracing. You can see that while we use some kind of the light source outside of the windows, we can see some kind of the bright, the indoor these things like this. And another example, you can see that some of the regions on the floor has some kind of the effect of the direct illumination, while also the parts of the floor and also the other objects have some kind of the colors, because they are also seeing some kind of the lights that are reaching to those points with some kind of the multiple reflections. So this is basically effects of the indirect illumination. Yeah, so in the global illumination, like one thing that we are going to see is that, so basically we are going to make some kind of the small change from the rendering equation that we have seen. So the rendering equation that we have seen was basically some kind of the reflection equation. So we are going to turn this into the light transport equation, which is almost the same, but we are going to see some kind of difference there. So basically the key principle during the light transport equation, LTE, here is basically the energy balance. Basically in the system that we are defining. So in the same thing that we are basically doing some kind of rendering, we are obviously going to assume that the difference between the power of the outgoing power and the incoming power should be basically exactly the same with the difference between the power which is basically emitted from the light source and also the power which is absorbed by some kind of the surfaces. So when you basically denote the power, the outgoing the power and the incoming power, and the emitted power, the absorbed power is kind of like those kind of things, then we can say that they should have some this kind of the relationship, right? And also, if we send the incoming the power onto the right hand side, then we can see that we also have this equation. So the difference between the incoming power to the absorbed power actually can be some kind of portion that we are seeing some kind of the some reflection, right? So when you see this kind of the equation, actually this is basically exactly the same that we are seeing with the rendering equation that we are seeing. So actually the rendering equation that we have seen in the previous slide was like having this kind of the three terms. So what we are going to do is that we want to basically compute the outgoing the radiance as kind of the sum of the emitted light and also the reflected light, right? So those are like basically three terms. So in the global illumination, one thing is that, so here the question is basically what should be the instant the radiance should be, right? So we basically separate this with the outgoing radiance in the previous case. But if we think about like what the kind of instant the radiance should be, basically here some of the assumption is that we assume that there is no basically the participating media, which means that the space is basically empty, right? So there's basically nothing, it's kind of the vacuum, the space. While the environment is basically not this kind of case. There is obviously some kind of the participating the media. So we are also going to discuss the volume rendering in the next week. But for now, let's assume that the space is basically empty. There's nothing there, the vacuum space, right? So in this case, we can assume that the radiance is basically the constant along a ray. Then in the global illumination, basically what we can assume is that the incoming ray, which is basically reaching to the point P from the direction of the omega I here, is basically the same, that which is basically coming from some kind of the other objects from the point P there, which is basically the first intersection point from the ray, which is shooting from the point P with the WI, the omega I here. So let's say like we are basically we want to get the information about the incoming the radiance from this direction at the point P along the direction of the omega here, right? Then actually this incoming radiance from at this point from this direction actually should be the same with the outgoing direction at this point, which is the first intersection point from this ray into the opposite direction, right? Very obvious, right? So basically in the global illumination, the way that we are basically going to calculate the incoming the radius is basically taking the outgoing radius from the previous the bounce, previous the deflection. So basically simply what we can do, so ray tracing is kind of the sort of the reverse engineering. We are basically back tracing all these kind of travels of the lights. So what we can see is that if we want to get the incoming radius information at the point P along the direction of the omega here, we just shoot a ray, find the intersection point here, and then basically take the outgoing radius along the opposite direction. So that becomes this term, right? So now we can replace the incoming radius term here with the outgoing radius in the scene. So that becomes this. So when you calculate the outgoing radius here, this is the same thing rendering the equation. While we are just taking that, this incoming radius term is kind of the outgoing radius from the first intersection point with the opposite direction. Is this clear? So then this is nothing, but also the kind of thing is that now then we are seeing some kind of the recursive deform. We are having the outgoing radius here and also here as well. So this is kind of the some recursive equation. So basically that makes the computation more kind of complicated, right? So in general, is there some kind of the analytic solution of this? Obviously, the answer is no, right? When you think about some kind of the complexity of like all the kind of light sources and also kind of the BRD and many kind of things, it would be really hard to basically derive some kind of the analytic solution for this kind of recursive equation. So that's why we are also going to use the Monte Carlo estimate in this case. But let's think about some very special case that we can somehow think about some kind of the analytic solution. So this can be like one specific example that we can think about some kind of the analytic solution. So consider some kind of the interior of a sphere as kind of scene that we are considering. And basically when you have this kind of interior of the surface, basically we assume that all the points of the surface have the perfect diffuse reflection, the universal reflection, which means that the BR depth becomes constant. So let's think of like this specific case. And also all the points are basically the big sphere is kind of the light source in terms of all the points where the sphere emits a constant amount of the radius into the all direction. So everything is the constant, both the BR depth and also the light emission. For this kind of the case, can you somehow derive some kind of the analytic solution of the light transport equation? So that's the question. So we are just like considering a special case that we can somehow come up with some kind of the analytic solution of the LTE. So basically, to compute this, you will need to check out the slide of like computing the irradiance in the previous lecture. So when you have some kind of the hemisphere, like how we computed the irradiance from the constant incoming radiance, you can recall what we have done in that quiz in the previous lecture. Did everyone get the same results like this? So here, like one actually important thing is that like while we had this kind of the discussion of the equation, actually is kind of a recursive form, which means that we need to think about like how the L is basically being updated for every single kind of the some iteration. So actually we can see that actually this is kind of the form of the Newman series, which is taking the sum of like this term. And the thing is that when you see this kind of the Newman series, this series only converges into some kind of a certain the finite number when this like this term, this c times the pi is one or the less than one. Otherwise, it will explode. Yeah. So this is not shown in this equation, but if we actually see that it's like recursive form, then you can see that actually this is the like this kind of the series, which is converging to this equation, and this can be also computed from the equation that we are seeing in the first row, right? So this is like very special case that we can somehow calculate the analytic solution to LTE, and also the things that we need to check out that actually this is kind of the recursive form, which means that some certain the situation actually the equation will explode, which means that the C should be basically some kind of the certain amount in terms of that the LT can converge into some kind of a finite number. So that can make some kind of the scene that we are seeing some kind of the energetic balance in the scene. But this is kind of a special case. For most of the cases, it will not be possible to basically have some kind of the analytic solution, and that's why we are going to also have some kind of the Monte Carlo estimate for the light transfer equation. And as we have seen in the previous slide, let's also convert this kind of the LTE into the area form. So we also converted the sampling with based on the solid angles into sampling with the set points over the area. So we can do the same thing in this case. So we are now rewriting this LTE into the so-called 3-point form. First, we are replacing the differential the solid angle with the differential the area, as we have seen in the previous slide. This is exactly the same. And these are like changing the notation. So the outpoint, so this is basically the case that we are seeing some kind of the right bit traversal from the P double prime to P prime to P. So the light goes in this way, while our the computation will be the reverse way. So obviously the way that we are doing some kind of ray tracing might be that we should be ray from the P and into along this direction, going into the opposite direction, right? Then the first intersection point, let's say the first intersection point is the P prime. And at this point, we are basically calculating the reflection from the points from the P prime, which is also from the another surface, right? So we basically go into this kind of like reverse way to traverse the trace the basically the light the trajectory, while the light is coming from the P prime to P double prime to P prime to P, right? So the outgoing radius becomes the radius from the P prime to P, and the incoming radius becomes the P double prime to P prime, right? And also the BRDF also has another the kind of the presentation that we are having the reflection from the P double prime to P prime to P, right? And also, as we have seen in the previous slide, we are also going to introduce the visibility term to check the occlusion from the P double prime to P prime, right? Then we can just like rewrite the same LTE with this kind of the new notations for each of the term. Then we're gonna see this kind of term. We can see that now we are having the new visibility term here, right? And also replacing the differential the solid angle here with the differential of the area here. To simplicity, let's also basically introduce another the kind of the term, which is the G here. Then we can also introduce the LTE into the area form like this. Make sense? Simple. Here, one quick question is that why do we only care about the visibility between the P double prime to P prime, but not the P and the P prime in this equation? Isn't it weird? We only care about the visibility between the P double prime to P prime, but not between the P and the P prime in this equation. Why? if you didn't feel that this is weird, then you either understood everything correctly, or you either didn't look into the details. A hint is that let's think about like what's the situation that we are calculating this equation. So we are basically doing some kind of a ray tracing, right? Yeah, so if I just briefly explain the things, so this is like the situation that actually we are starting from the point P, and then we are shooting the ray along the opposite direction of the omega and the R here, right? And the first intersection point was the P prime. And now we are calculating the reflection at this point to compute the outgoing direction, the radiance from the P prime to P. And then we're gonna do this kind of like, recursive way. From the P prime, we're gonna also shoot a ray along some specific direction, and then we can also do these kind of things, right? Which means that in this kind of ray tracing the computation, like P prime, it was basically the first intersection point from the P. And that is the along this direction. So that is the reason like why we are calculating reflection at this point at the P prime. So which means that if this P prime was not visible from the P, then we don't need to compute the reflection at the P prime. Then we will basically have another the first intersection point, and we will calculate the reflection at that point, right? So obviously, if we are calculating the reflection at the P prime to the direction of the P, which means that P prime was basically the first intersection point from the P when you basically do this kind of ray tracing. So which means that there was no occlusion. Does it make sense? So think about basically how we are basically doing some kind of ray tracing. So we are starting from the pixel of the image plane, shooting a ray into a certain specific direction, and then finding the intersection point. So let's say, like for example, like P was actually kind of the point of the image plane, and the P prime is basically the first intersection point along that direction. And then we calculate the reflection at the point P prime by considering all the other kind of the rays from the P double prime. So we are calculating the reflection at the P prime because that was the first intersection point from the point P, which should be visible point from the P. So if it was not visible point, then we obviously should have another intersection point, and we should calculate the reflection at that point. So that's why we don't need to have the visibility term between the P and the P prime, right? That makes sense. So we need to think about basically how this equation will be exactly implemented in our ray tracing system. So yeah, think about this kind of like ray tracing the system. So basically, we're going to have this kind of like some recursive form. We are starting from the P0. So this is the P0, which is the point at the image plane, finding the first intersection point, which is the P1. Then we're going to have this kind of the LTE equation from the P0 to P1. So we are doing some, tracing the rays in the opposite direction, right? So we are going from the P0 to the P1. And for that, actually, we are calculating the outgoing radiance from the P1 to the P0, right? For this computation, actually, we're going to have these two terms. Well, one is about the emission, and the other is for the reflection, right? Then we're going to also have this kind of the term, which is from the light from the P to the P1, right? For all the light for the P to the P1, actually, we can also replace this term with another the LT equation like this, right? So which means that we're gonna have some kind of the this kind of recursive form. So we rewrite everything, then we're gonna have this kind of form, taking the multidimensional integral with some kind of the subsequent terms like this. Then we can say that the first term here becomes of the path of the length 1. So we are basically seeing some kind of the direct the light emission the terms here. The second one becomes the direct illumination with the single bounce with the path of the length 2. And the third case is starting to see some of the cases of the indirect illumination with the length of the 3, and we're going to also some more of the terms. So you can check out the equations like, substitute this term here with the LT formulation here, then we can see that this kind of the output, and also like recursively like replacing all the things. And the same equation also can be rewritten like this. So when this P n bar is kind of the trajectory of the n plus 1 number of the points over the scene, then we are basically calculating this kind of the outgoing the radiance from the trajectory, which has this kind of the equation, taking some multiple the integral in the multidimensional space. And also for the simplicity, we're gonna name this term as kind of the throughput of the path, which is denoted as the T, which is, you can see that this equation basically has the meaning of the like calculating the reflection of the light from the light source at the end point of the trajectory, reaching at the kind of the first point at the image plane. So that becomes like this complicated formulation. So in the simplest case, the way that we can calculate this is that we can think like we are shooting some kind of the multiple rays, like having some kind of the loss of the trajectory, and that becomes basically one of these kind of the P case here. And each of the P equation with the trajectory can be estimated. The simplest case with the single the trajectory with the single sample of the path. So we have the Monte Carlo the estimate for each of the P here, and then the light coming from this specific direction into the pixel P0 at the image plane actually can be computed as this kind of the sum of the single sample the estimate of the Monte Carlo the estimates from kind of multiple trajectory. So this will be kind of the basic idea of like taking the integral of the multiple paths, which sounds kind of like quite complicated, right? But basically, I recommend you to basically get the sense of like what we are doing with this equation. And this will be also basically the basic idea or like what we are also doing in our the programming assignment in the path tracing. So the programming assignment will not basically involve the part of like implementing some parts of the path tracing, but I strongly recommend you to check out how exactly this path tracing is working. And also that is kind of like the simplest version of the path tracing. And if you want to see some kind of the complete version of the path tracing, I also strongly recommend you to check out this book, the physically based rendering, which has all these contents online publicly. So you can check out, even you don't need to buy the book. You can just check out every content here. And also the good thing of like this textbook is that this book does not only show some kind of the equation, but also explains how exactly all these kind of things can be implemented in code in C++. So I also strongly recommend you to check this out and get the sense of like how this kind of the Monte Carlo estimate with the multiple passes are basically implemented in code. So next time you're gonna see some more details about like how exactly we do the path tracing, and you're gonna also discuss some kind of the reflection models. And next week we're gonna move on to the volume rendering and also some topics in the neural rendering as well. That's it for today. Any questions? So if you have any other questions, please post the questions on Slack. We can also discuss more on Slack. So I will see you next Wednesday. Okay. Thank you. Bye.